Hey guys, today we're going to talk about the effect of molecular structure on acid-base properties. All right, so you'll notice here we have tetrahedral shape, differences in the types of bonds that are present, particularly between the carbon and hydrogen, and between the carbon and the chlorides. All right, so it says what structural properties of a molecule cause it to behave either as an acid or a base. All right, first of all, the presence of hydrogen atoms, right? So any molecule that contains hydrogen is potentially an acid. But notice that word is in green. Just because it does contain hydrogen doesn't mean it's going to yield it. All right. So many molecules don't exhibit acidic properties. Why not? Well, we got to investigate two things. Number one, the strength of the bond, right? Where that hydrogen is being held within the molecule and the polarity of the bond. Okay, so we're going to be looking at those two components, and we're going to throw a little electronegativity in there as well. All right, first, strength. In general, the stronger the hydrogen, and by hydrogen bond, I mean the hydrogen, that's bonded to the site of the anion. All right, so the less likely the bond is to break to form hydrogen ions, right? So if it's less likely to break, the less acidic the substance is going to be, right? Because it's going to decrease the concentration of hydrogen, right? So if you look here with the halides, everybody go find the halides in group 7A, and you'll notice here we have hydrofluoric, hydrochloric, hydrobromic, hydroiodic, all right? You'll notice here a measurement in kilojoules per mole of the actual bond energy, right? The bond energy, as we go from top to bottom, is decreasing, right? So what does that mean? Well, it actually means that the hydrogen bond site, right, is getting weaker and weaker and weaker. So, right, the stronger the H bond, right, where this hydrofluoric is, right, the less likely that bond is to break. Right? It's going to be held together more. It takes a lot of energy to overcome that. Right? It's also more polar. Okay, so if you think back to electronegativities, fluorine being the most electronegative, right? Cesium, francium being the least electronegative, right? Remember that trend from first year. So again, we're noticing differences in bond energy, but also differences in polarity, moving from more polar to less polar if we actually investigate the differences in electronegativity. Oh, there's that word I just said. Remember, the electronegativity decreases, right, as you go down a group or family. If you think about this being hydrofluoric, all right, and then keep moving down, hydrochloric, hydrobromic, hydroiodic, right, that HF sharing, this bond right here, is very, very strong. It's super difficult to break, right? Look back at your energy value, your bond energy there, right? So it's much higher. And so that energy is decreasing, right, as you move down. And so the bond strength is decreasing. You have a higher tendency to yield hydrogens the further you go down, right? The hydrogens up here are super reluctant to dissociate in water. So if you don't have any hydrogens, right, I'm not affecting the acidity, all right? Now, we just looked at this picture on the top right on this slide. If you'll notice for just a second the difference in the size of these molecules, right? Clearly, as the size of the atom is getting bigger from top to bottom, right? Here's our hydrogen here, hydrogen, 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 fluorine, chlorine, bromine, iodine, right? So the size of the atom is increasing. Right? Let's look. It says the larger the atom that's bonded to that hydrogen, okay, larger the atom is bonded to the hydrogen, the weaker the bond, okay, oops, excuse me, the weaker the bond, right? So if we look here, the larger the atom, the weaker the bond, aka more hydrogens are going to be ionized or yielded, right? Why is that? Well, you have 50 bajillion hydrogen orbitals beginning to overlap as you have multiple molecules coming into contact with one another. And so you have all these 1s orbital business. So lots of electrons are, the hydrogens, the electron clouds are beginning, dense fuzzy clouds are beginning to overlap. Okay. So a bond between hydrogen and a really large atom like iodine or even tellurium is going to be weaker than a bond between hydrogen and a really small atom. Okay, so here's like hydrogen and fluorine, hydrogen and iodine would be way down here. All right, so this is weaker, this is stronger. So a general trend is that as we go down a column or family, said the acid strength of a binary hydride, okay, so like hydrofluoric, hydrobromic, hydrochloric, hydroiodic, right? Those dudes are going to increase. The acidic strength is going to increase as we go down the column, okay? General trend. Now, we can investigate other acids that have the presence of oxygen and look for some trends there, okay? This family or group are called oxyacids. They just have one or more oxygen-hydrogen bonds present, right? So you're looking for hydroxides here, okay? Now, you'll notice over here, all right, the presence of that oxygen-hydrogen bond, all right? You'll notice down here, here's a presence, and there's a presence as well. Water falls into this category because it does have an oxygen, hydroxide group bonded. Now, we're going to be looking for these groups that are bonded to central atoms. So here is a central atom. This is where we're going to be investigating. Here's our sulfur. That's considered the central atom of this molecule. All right, and we have that hydrogen here being bonded. So let's go see what's going on with these oxyacids. Okay. We can also look at them for a reflection of strength, right? So the acid strength is going to increase as the number of oxygens bonded to the central atom also increases. Well, duh, all right? So we have lots of stuff going on here, moving from hypochlorous, chlorous, chloric, perchloric acid, all right? Take a note. Here's our central atom. Chlorine is going to be the central atom for each one of these. So here you have one oxygen, and here's that hydroxide group right here. Here's the hydroxide group around the central atom, and an additional oxygen. So according to our statement over here, the strength increases as the number of oxygens bonded to the central atom increases. All right, so you've got that hydroxide group here, and then you have additional oxygen, another oxygen. All right, and then whoa, whoa, boom, boom. Okay, so the acid strength increases as the number of oxygens bonded to the central atom increases. Why is that? Well, lots of reasons, but let's try to think about this. Electronegativity, right? Electronegative oxygens. Okay, go put your eyeballs on the screen. Or sorry, go put your eyeballs on the periodic table. Go find oxygen, right? He's super electronegative. So electronegative oxygens, let's go find them. Oxygen, 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 oxygen. Whoa, 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 whoa. Okay. These electronegative oxygens are going to draw electrons away from less electronegative atoms. What does that do? Well, it diminishes or it decreases or weakens the bonds, all right, of the remaining less electronegative atoms. So it's going to weaken that oxygen-hydrogen bond, so that hydroxide bond. But in doing so, and kind of pulling on those electrons, it's also going to make that end of the molecule slightly more polar. So it polarizes the hydroxide bond as well. So what does that mean? What's that got to do with the strength of an acid? Well, here it comes. Hydrogen proton, therefore, is more easily produced by the molecule with the largest number of attached oxygens, okay? Because these oxygens are going to be pulling away. This is super electronegative, right? The difference between hydrogen and oxygen, right? The difference between hydrogen and oxygen, look at the number. So we have 3 oxygens here. You have 4 oxygens here, right? You have 2 oxygens, just 1 oxygen. So what's going to happen is that these super electronegative oxygens have the ability to pull this additional, aka freeing this hydrogen more readily. So if you have more hydrogens being ionized, what happens to your strength? You're increasing in your strength as well. Okay? All right. So we've looked at the strength of the bond. We looked at oxyacids. We looked at polarity. All right. Let's look at one more. Covalent oxides. All right. So we're going to look at covalent oxides that, when dissolved in water, will yield acidic solutions called acidic oxides. All right. Lots of examples of these that you already know. All right. Sulfur trioxide, for example. This is a covalent oxide. Did you hear the words I just said? Sulfur trioxide. Go back to your old school. Two nonmetals stuck together. It's covalently bonded. All right, gotcha. When sulfur trioxide gets dissolved in water, it's going to yield, oh, look at that, sulfuric acid. All right. Here's another example. Carbon dioxide. Okay, covalent oxide dissolves in water, generates, hey-o, carbonic acid. All right, so those you're super comfortable with. All right, now come down here and let's look at these. What if I have an ionic oxide? All right, so here's calcium oxide. Remember, calcium is a group 2 alkaline earth. And here we have this ionic oxide being dissolved in water. So when that happens, if you think about it, one way that Miss Freeman always told you to remember double replacement reactions is HOH, right? So what's going to happen here is that water is going to actually act as the acid and donate a hydrogen to this ionic oxide, yielding calcium hydroxide. Okay. Same thing over here with potassium oxide. It's going to yield potassium hydroxide. Okay, so it makes sense to think about this hydroxide, right, creating a basic solution. I'm not done. I don't know why that happened. Oh, maybe I am done. Oh, I am. Well, kudos to you. You survived my first, whatever this thing is called with the QuickTime player, voiceover. And as you can hear, it's time for me to go to bed now. So hopefully you guys will get some additional assistance from the tutorial videos that I put online. So take some time to look over those today. Get your earbuds out. Watch that awesome video, okay, on the Wikispace. If you go to our homepage. All right, it says watch this on acid strength, okay? All right, take a moment to look at that. You can be working on some WebAssign afterwards. We also have the titration curve practice. You can be using Loggerpro for that. Once you just create a titration curve, we may have to abandon our sad little titration lab. See if I can come up with something else. Time is getting away from us. We had the ACT, and now I'm absent, blah, blah, blah. All right, so we'll see what's going to come up with that. All right? Hope you guys have a good day. I'll see you on Thursday.